So in physics, we have a process called induced EMF, and this induced EMF depends on a concept called magnetic flux. So to know about induced EMF, we first need to understand what magnetic flux is. So what is flux? Well, a flux in physics is just a change in something. It implies that something is changing in a quantity. And the magnetic flux has a very specific definition. It uses the equation, the Greek letter phi, that's equal to B times A times cosine of theta, where each one of these quantities means something. B is the magnetic field. That goes through an area. A is the area that your magnetic field goes through. And theta is the angle between B, your magnetic field, and A, the area that you're going through. So what does that actually mean? What does that look like? Let's say I have a hoop, and this hoop is sitting inside of a magnetic field. And the magnetic field is going through like this. So my magnetic field lines, represented by these kind of horizontal lines, those are B, that's my magnetic field, and they're passing through this area, this hoop. So whatever the surface area of this is the area that I'm talking about. And then theta is the angle between the magnetic field, so in this case these horizontal lines, and the area. And not just any part of the area, we actually want to be perpendicular to the area. So a line that's perpendicular to the area. So if I have this particular shape, the line that's perpendicular to this would be going kind of to the right or to the left. So I need to get the angle between the magnetic field and this perpendicular line that's at a 90-degree angle to my area. Other important thing to talk about with physics is the actual units that we're talking about for magnetic flux. So the units of magnetic flux have to be equal to the units of magnetic field times the units of area times the units of the cosine of the angle. Well, right away we can eliminate the cosine of the angle. That has no units, it's unitless. The units of area we can write, and the units of B we can also write. So the units of B are Tesla, units of area are meters squared, and that gives us the units for a magnetic flux. Units of magnetic flux are Tesla times meters squared. So we should know this equation for flux, B times A times cosine theta, which is the amount of magnetic field lines that are passing through this given area that we see down here. And also the units of magnetic flux, phi, are equal to Tesla times meters squared. So how do we use this magnetic flux and why do we care? Well, anytime we change the magnetic flux, this phi, this is going to induce, this is where that word induction comes in, some kind of EMF or a voltage. Remember, EMF, electromotive force, is code word for also voltage. Okay, so if I change a magnetic field, I can create a potential. And this brings us to Faraday's law of induction. We have one way that we can get an induced EMF. So we'll call this induced EMF process number 1. And this happens inside of a coil. So let's say I have a coil of wires. This is often how we see wires kind of wound up into a little coil. I can induce some EMF. EMF can be induced that's equal to negative the number of actual coils that I have times the change in flux that's going through those coils divided by the change in time, how fast those fluxes are changing inside of this coil. So we should make note of what all these variables are. N is the number of coils inside of your wire loop. So for this particular example, I can see there's 1, 2, 3, 4, And we'll finish up that fifth little coil down there. So the n would be equal to 5 for this particular picture that we have. Then we have some change in phi and some change in time. So how fast a magnetic flux is changing. And we need to remember that this magnetic flux equation is B times A times cosine of theta. So I might have a changing magnetic flux by, let's say I have, maybe I have a strong magnetic field with 3 lines going through this loop going up, and then I actually turn down my magnetic field so that I'm creating a smaller magnetic field. So this would mean that I would get rid of one of those lines. So if I turn down the magnetic field, I can eliminate this middle line maybe. And when I erase that middle line, I've gone from 3 lines. Now I only have 2 lines going through this kind of coil of wire. So because I only have 2 lines now, I have just changed this flux. I have changed the B times A times cosine theta, and that's going to induce an EMF. It's going to induce a voltage inside of this. The last key point to make here is this negative sign. This negative sign is something called Lenz's law. And what this tells us is that the change in flux that's created inside of this, the EMF that we get, change is resisted. Okay. So the EMF that I create in here, the induced EMF, will create a current that resists your change. So I'm going to create some current inside of this hoop, inside of this coil of wire, that's going to try to resist the change that happened. The change that we just saw was we got rid of one of these magnetic field lines. We went from 3 down to just 2. So I'm going to create some induction, and that induction is going to try to create another line that's going up through this to give me a new magnetic field to resist that change. It turns out that the magnetic field, the current that I would create, would be going through the loop in kind of this direction. Okay. If that doesn't make sense, you can take a look at the book, or you can submit questions through the discussion boards, and we can go over that in lecture potentially. That's basically the first induced EMF approach that you can have. There are others. So another way that you can induce some EMF is with actual movement. So instead of changing the actual magnetic field, you can actually make the magnetic field move. If something moves in a B field, if we start moving inside of a B field, that means that the flux is going to change that's going through it. Flux changes. You're basically either changing the B, number of magnetic field lines, or you're changing the A. And if flux changes due to this motion, then you induced an EMF. And we can quantify this with an equation as well. So this is a process called motional EMF, motional EMF. And it's defined as E is equal to B times L times V, where E is your EMF, or your voltage that you create, the potential that you create. B is the magnetic field. L is going to be the length of the object that's actually moving in your magnetic field. And V is the velocity of your object, how fast your object is actually moving. So maybe I have a loop of wire, and I'm going to send it moving through a magnetic field. And it's going to be moving maybe this way to the right. So as I'm moving through this, I have my 3 magnetic field lines. So I take a look at this little loop a little bit later, and a little bit later it has moved now. Okay, so I've gone from having 3 lines at the beginning to just 2 lines at the end. So I've changed the magnetic field. I have a new magnetic flux. So that gives me a motional EMF. This EMF is B times L times V, the velocity that you're moving at. This kind of application it turns out to be very important. It's important in a lot of medical applications, where once you take some kind of object and you start moving it inside of a magnetic field, let's say for an example, maybe inside of an MRI. So in an MRI, you're moving people, patients, which actually have electrical currents moving around through them, and you're moving them in and out of a magnetic field. By doing that, you are inducing some EMF. You are inducing voltage in a patient. So you have to be cognizant of what you're actually doing. You have to understand the physics going on, because this motion is going to induce voltage, which is going to create current going through your actual patient. This current has a specific name. We call these currents that are induced eddy currents. And they happen because of this motional EMF that's created by an object just moving inside of a magnetic field. The final equation that bears mentioning is EMF being induced inside of an electric motor. So EMF inside of an electric motor is equal to N, capital N, times A, times B, times omega, times sine of omega t. So you need to read in the textbook about this, but to describe what all these variables are, N is the number of turns inside of a coil inside of your motor. Same as it was before. A is the surface area, cross-sectional area of your coil of wire inside of your motor. That's the area of your coil. B is the strength of your magnetic field. And the units of that would be the units of magnetic field, which are just Tesla. Just as a reminder. And omega is the rotational velocity. So how fast your electric motor is going to be spinning. And you can get more details from that from your textbook. So that's kind of induction in a very, very quick nutshell.